Another example is that of a curve, a parabolic curve, which tends to open downward. For the function graph in figure 7-2G, letter A, identify the kind of function it could be. Letter B, on what interval or intervals is the function increasing or decreasing, and is the graph concave upward or downward? Letter C, describe something in the real world that a function with this shape of graph could model. Letter D, find the particular equation for the function given that points 176, 289, and 394 are on the graph. Letter E, confirm by plotting that your equation gives the graph in figure 7-2G. So we would answer the first question. What kind of graph is this? The one that you could see. It's a curved graph. And from our experience, this type of function is actually, this is a quadratic function, right? So this one is a quadratic function. Okay, why are we so sure that this is a quadratic function? Based on the examples I gave you, if you see a curved graph which has a concavity of downward or upwards, and it looks like this, a mountain or somewhat like inverted, then these types of graph are always quadratic. They have a minimum limit, or rather a minimum point and a maximum point on the middle, which defines their axis of symmetry. So this type of function is a quadratic function, and no question about that. Letter B, on what interval or intervals is the function increasing or decreasing? So, seeing the graph on the right, okay, the one at our right, we could see that this function is increasing. It's increasing for x less than or equal to 3. Now this is the axis of symmetry. We have to label it. Let's make it more accurate by labeling our axis of symmetry. So this axis of symmetry is important in determining the domain for which the graph is increasing or decreasing. So as we notice, it is increasing when x is less than 3. And also at the same time, it is decreasing when x is greater than 3. And it has a maximum point when x is equal to 3. And the maximum height that it could attain is 94. That's why we have point 394. So at x is equal to 3, we have a maximum point of y is equal to 94. And is it concave up or concave down? Now, at this interval or at this domain, x is less than 3, we have a pattern, a graph that tends to go down, so it opens downward. And also, at the same time, at x is greater than 3, the graph is also opening downward. So, over the entire domain of this graph, the function is concave down. So concave down over the entire domain. Okay, letter C. describe something in the real world that a function with this shape of graph could model. Number 3, our answer for this question is any realized equations that could express a parabolic curve, a trajectory of a parabola, such as kicking a football, let's say, kicking a football from, of course, a certain height, which is here. So kicking a football at that height, what else? Shooting an arrow, yes, that could also be possible. At a certain height, you shoot an arrow, and it will land somewhere over the entire, at the end of the domain. So from this point over this point, and for example, if you start here, then the shooting would end here at this before it hits the ground here. So that would be from here to here, that range. And you could tell that shooting an arrow is another example. Letter D, find the particular equation for the function given that points 176, 289, and 394 are on the graph. So we have a specific points here. What are those points? First point is 176, so let's call it A, 176. B, we have 289. And C, we have 394. Now since we already defined this as a quadratic function, a quadratic equation, okay, then we are going to use the general form of the quadratic equation in solving the proper equation for this type of graph. So what is the general equation of a quadratic function? That is y is equal to ax squared plus bx plus c. And substituting the values for x and y for these 3 points a, b, c, then we are to get, for the first point A, that would be 76 is equal to, our x is 1, so that would give us A, because 1 squared is just 1, plus B, plus C. For B, we could have 89 is equal to 4A plus 2B plus C, because C is constant. And for letter C, we have 94 is equal to 9A plus 3B plus C. And we are going to solve for A, B, C, so we have 3 unknowns. And a requirement for 3 unknowns should be, we also must have 3 equations. And we get it, we have 3 equations. But how do we solve this? There are 2 ways to solve equations with 3 unknowns. First is doing algebra, and secondly is by doing the matrices. So since your calculator has a property to solve for matrices, then we could actually use your calculator in order to solve for our 3 unknowns A, B, and C. So A, B, and C. And on the following video, I am going to present to you how to solve the unknown variables A, B, C by the use of matrices, which are a part of your calculator system. So here we go. In the previous slide, we have already noted that this is our function. We have, and these are our equations, on which we have 3 unknowns for every point that we assign to the general form of our quadratic function. Y is equal to ax squared plus bx plus c. And let us now see how to manipulate this equation in terms of the matrices. Now notice that the coefficients on the right side form a 3 by 3 matrix. So we have, for A, B, C, we have 1, 1, and 1. For the second equation, we have 4, 2, and 1. 4, 2, and 1. And for the third, we have 9, 3, and 1. So therefore, we have a 3 by 3 matrix. Now let's take a look at the right side. We have 76, 89, or rather on the left side, 76, 89, and 94. The y values on the left side form a 3 by 1 matrix. So as you can see, we have 76, 89, and 94. We have 3 rows, or rather 3 column and 1 row. So how do we put this into your calculator? This 3 by 3 matrix and this 3 by 1 matrix. So looking closely, we could set the calculator into the matrix mode. We have second F and x negative 1. So that would be your matrix. And we could edit our first set of matrix. We have a 3 by 3 matrix. So we have a column of 3 and a row of 3. So we are doing it now, and let's enter it, and let us put all of the values of the equations. So the first equation, we have 1, 1, and 1 for A, B, C. For the second one, we have 4, 2, and 1. And for the third one, we have 9, 3, and 1. So that forms our 3 by 3 matrix, which defines our A, B, and C. Okay, so we're going to create the matrix, the first matrix. We go to the second matrix, call it B, and we are going to input a 3 by 1 matrix, 3 for a column and 1 for the row. So we have values of, for the first value, we will enter 76, and make sure you enter the y values in the same rows as the appropriate coefficients. Okay, otherwise you would get different answer. So our matrix B is a 3 by 1 matrix with 76, 89, and 94. So that's how we edit our set of matrix for the left part. Now we are done with our 2 matrices. Okay, we could now set our inverse coefficients. So A to the negative 1, that will give us the product of your matrices A and B. So A negative 1, B, which will give you negative 4, 25, and 55. Therefore, we have the values for A and B, which is equal to negative 4, 25, and 55. And that would give us the equation for the quadratic function that we are finding. So negative 4, or A is negative 4. So let us put it here. According to the matrix computation, A is negative 4, B is equal to 25, and C is equal to 55. I am now substituting my values for A, B, and C with respect to the original equation. Y is equal to ax squared plus bx plus c. So I got negative 4x squared plus 25x plus 55. So this is our equation. This would be our equation. Okay? Now, what is the last question? Confirm by plotting that your equation gives the graph in figure 7-2G. To confirm wherein our graph really confirms this graph presented here, we have to analyze our general equation for this type of graph. Now our graph or our function equation gives y is equal to negative 4x squared plus 25x plus 55. And we have two properties that could be derived from here. The first property is that, look at our A. Our A is negative 4, and E is negative 4 is less than 0. And in our description of the properties of parabolic curves, when our A is negative or less than 0, the function opens downwards, so which confirms that our shape for this type of function, y equals negative 4x squared plus 25x plus 55, is actually opening downwards, and its concavity is downward also. And what's the second condition? You could see that our y, or rather our y-intercept, is somewhere below 60 and above 40. So our y is equal to, this is our y-intercept by the way, okay? Y is equal to 55, which is in between our 40 and 60. Makes sense also. Okay, because noting the fact that we have A is equal to negative 4, which is less than 0, opens downward, and we have a y-intercept at 55, y is equal to 55, it makes sense. So therefore, using those two observations alone could make us confirm that our graph indeed gives the graph of the curvature that is being presented here on this page. So therefore, that's our answer for letter E.